Good morning, everyone. My name is Yulin. Today I will present the work on future global river ice in CMIP6 model under climate change. River ice is essential for northern regions, and its response to warming affects both communities and ecosystems. River ice is a key part of the cryosphere. It controls river flow in winter and spring, affects floods, and supports ecosystems. It even provides winter roads and platforms for construction, something many northern communities rely on. But global warming is changing this picture. Ice seasons are getting shorter, ice is getting thinner, rivers have more open water. This can shift the timing of runoff and increase the risk of ice-range flooding. River ice also act like a lid on rivers, trapping greenhouse gases below. When the ice disappears, more CO2 escapes into the atmosphere. So, understanding how river ice will change in the future is not just a scientific question. It's essential for water management, for the safety of northern communities, and for climate research as a whole. Compared with CMIP5, CMIP6 shows a stronger global warming signal and does a better job at capturing extreme events. So, it gives us a more reliable basis to estimate future river ice changes. But here's the thing. Most past studies still focus on specific regions or river basins. Very few have looked at global river ice loss or measure how sensitive river ice is to warming. And the shift from ice cover to ice-free rivers hasn't really been studied in a systematic way. So, our study tried to fill this gap. We asked three key questions. First, how will river ice extent and duration change globally under CMIP6 warming? Second, how sensitive is river ice to temperature rise across different regions? And third, where are the hotspots of future ice loss? These are the questions that motivate our work and guide the analysis. I will show you next. To answer these questions, we first use CMIP6 model. We focus on surface air temperature and look at two scenarios, SSP2-4.5 and SSP5-8.5. For the time period, we look at the near term, from 2017 to 2044, and the long term, from 2073 to 2100. Out of the 20 available CMIP6 models, we select these three models based on two conditions: high resolution and a wider range of global mean SAT variability. For the river network, we use the Global River Width from Landsat database. We include river wider than 90 meters with a single channel and no lake influence. To estimate river ice extent and duration, we applied a logistic regression-based river ice cover model. This model links the probability of ice cover to the 30 days prior mean temperature and whether it is freeze-up or break-up season. In this model, February to July is treated as the break-up season in the northern hemisphere and as the freeze-up season in the southern hemisphere, with the rest of the year flipped accordingly. The model's coefficients were calibrated with historical data, and is reproduced as on and as off days quite well at the global scale. Altogether, these data and models allow us to simulate future river ice extent and duration, compare the two scenarios, and analyze regional differences. Now, let me introduce the key regions and the workflow of this study. First, we identify key regions that account for the top 20% of global river ice change. In order to better evaluate the impact of climate warming on river ice change in these key regions, we also calculate and analyze both river ice change and mean SAT change for each subregion. The division of these 41 global land subregions carefully consider climate consistency, model performance, scientific and policy needs, and the requirement of international climate change assessment reports. By selecting just the key regions, we are able to focus on the area with the largest change and study their temperature sensitivity in more detail. This approach makes our analysis more targeted and meaningful rather than averaging everything across the globe. On the right, you can see the workflow of our analysis. We start with CMIP6 temperature data under the two scenarios and the global river width from Landsat. This input will then fed into the river ice cover model, which estimate river ice extent and duration for each river glacier. This step is crucial because it converts climate data into something that directly tells us about ice conditions. Next, we use this output for three main analyses. First, we look at the change in river ice extent and duration under both scenarios, for the near term and the long term. Second, we explore the relationship between river ice loss in the key regions and temperature change. This helps us assess how sensitive river ice is to warming in different parts of the world. Third, we examined future monthly river ice changes. Altogether, this workflow allows us not only quantify the further river ice loss, but also to understanding regional pattern and climatic drivers. This combination of global coverage and regional detail is one of the strengths of our study. Now, let's look at the global river ice change under SSP 2-4.5. Compared with the near term, the long-term warming is about 1.1 to 2.5 Celsius degrees. This warming leads to a reduction in river ice extent by 1.9 to 4.4 percentage points, and a shorter ice duration by 6.8 to 15.1 days worldwide. So, overall, rivers are losing ice and the ice season is getting much shorter. We also see that the proportion of ice-free rivers increased by about 1.7 to 4%, which means more rivers will stay open through the winter instead of freezing. If we look at the figure on the right, it is simulate river ice extent change between near and long term. We can clearly see where the losses are happening. The largest river ice loss occurs in North American, European, the Tibetan Plateau, and part of Siberia. These areas are especially sensitive to warming. Different regions also show distinct spatial patterns. For example, in some places, the decline is stronger from coastal areas toward inland regions, and in others, from higher latitude toward lower latitudes. This means the impacts are not uniform, and some regions will be affected much more severely than others. So, under SSP 2-4.5, we see a moderate but widespread decline in both river ice extent and duration with pronounced spatial heterogeneity. This highlights the importance of looking at regional differences rather than just global averages. We compare the long-term change in river ice between SSP 2-4.5 and SSP 5-8.5. First, under SSP 5-8.5, the projected warming is about 1.5 to 2.3 Celsius degrees higher than under SSP 2-4.5 by the end of the century. This stronger warming leads to a greater reduction in river ice extent, about 3 to 4.7 percentage points, and a shorter ice duration by 11 to 17 days compared with SSP 2-4.5. So, the ice season becomes much shorter. The proportion of ice-free river increased by 2.2 to 3.8%, especially at mean latitude between 40 and 60 degrees north, where many rivers are projected to become completely ice-free during winter. If we look at the figure on the right, we can see that the largest river ice loss is concentrated in northern, western, and northeastern North America, Europe, the Tibetan Plateau, and part of Siberia. These regions show very pronounced reductions, with some rivers losing almost all of their seasonal ice. Importantly, when we normalize this result by the temperature increase, the cross scenario change per Celsius degrees warming is about 1.1 to 1.3 times larger than the near to long-term change within SSP 2-4.5. This means river ice respond non-linearly to warming and is more sensitive under high emission scenarios. Overall, this result suggested that high emission pathways could drive a much more severe transformation of global river ice regimes, accelerating the transition toward ice-free conditions in many rivers. Here, we use CMIP6 as an example. Among the selected model, this model shows the largest surface air temperature rise under SSP 2-4.5 from the near term to the long term, which make it a good case to highlight regional variability. If we look at the figure on the right, we can see there is stronger heterogeneity in both warming and river ice loss. The largest warming occurs in northeastern North America. The largest reduction in river ice extent is found in Eastern Europe. And on the Tibetan Plateau, we see the highest sensitivity, mean large river ice loss even through the temperature rise is relatively small. For river ice duration, Eastern Europe lost about 37 days, followed by the Northern Europe. Overall, the losses tend to decrease from coastal to inland area, and from high latitude to low latitudes. When we compare key regions, the top 20% of global river ice change within non-key regions, we find that duration dropped by 34 to 51 days in the key regions, but only for 2 to 23 days in the non-key regions. This clearly highlights the greater vulnerability and variability of coastal areas, mountainous regions, and high-latitude zones, such as the Russian Far East and the Russian Arctic region. Altogether, this example shows how regional differences matter and why it is important to look beyond global average when assessing the impact of climate warming on river ice. After examining the regional differences, it's also important to see how this change evolved throughout the year. As we can see in the figure, there is a strong seasonal pattern. The strongest warming is projected from October through March. At the same time, the largest reductions in river ice extent occurs from October to the following June. So, most of the ice loss happen during the main freeze-up and break-up season. Within these 9 months, the most sensitive period are April, May, November, and December. During this month, for every 1 Celsius degrees rise in temperature, the global river ice extent decreased by about 0.7 to 3.9 percentage points. This means that even a small temperature increase can lead to a substantial river ice loss. Overall, this result tells us that continued warming will accelerate month river ice decline. We will see shorter ice seasons, early breakup, and delayed freeze-up, which can have important consequences for river hydrology, flooding, navigation, and ecosystems. Why do river ice change vary by region? The river ice cover model shows a nonlinear temperature-ice relationship with the highest sensitivity around -2.3 Celsius degrees. Regions near this temperature, like Eastern Europe, can lose a lot of ice with just a small warming. Globally, large ice losses happen where temperature lies in this sensitive range and where warming is stronger than in other regions. Local geography, coastal, peninsular, mountains also shape temperature, which amplify these differences. Together, this explains why some regions lose ice quickly under moderate warming, while others are less affected even with bigger temperature rise. Here we look at how sensitive river ice is to global warming. For every 1 Celsius degrees rise in global mean temperature, the global river ice extent dropped by about 2.1 percentage points, and the ice duration shortened by about 8.4 days. Both of these declines are larger than World CMIP5 project, which show that CMIP6 captures stronger warming and bigger impacts. For every 1 Celsius degrees rise in global mean temperature, the river ice extent decreased by about 2.1 percentage points and the duration shortened by about 8.4 days, both larger than CMIP5 projections. Under SSP 5-8.5, the losses are even greater, with ice duration declining 1.1 to 1.3 times more than under SSP 2-4.5. The largest losses occurs in North America, Europe, Siberia, and the Tibetan Plateau, especially in coastal and mountainous regions. Future study will include precipitation, flow, and topography, and use more models to reduce uncertainty. Thanks for your listening.